So welcome to the last of the 4 sessions in this room for today. So the last one is, again, on a slightly different topic, but it's a sort of general design support topic on ESD. It's going to be presented by Dr. Shih-Hung Chen, who is at present with IMEC. He received the MS degree from National Shih-Hung University in Hsinchu in Taiwan in 2002, and the PhD degree from there in 2009. In 2002, he joined the Department of ESD and Product Engineering at the SICC Technology Center, Industrial Technology Research Institute at Hsinchu. And since 2010, he's been with the Device Reliability and Electrical Characterization Group at IMEC. He's been involved with IRPS, the ESD Symposium, and ISQED. His current research interests include ESD correction in advanced sub-10 nanometer technologies, and that's what he'll be talking with us today. So let's please welcome.
Okay. So thank you, Colin, for the introduction. So good afternoon, ladies and gentlemen. So in this tutorial, we will look at the ESD challenge in advanced CMOS technology node. We will mainly focus on the designed dial-based ESD protection because the dial is the most efficient and the simplest ESD protection device, and they will not impact too much by the layout parameter or different layout style. So it will be good access to understand how technology option or process option impact ESD performance. Okay. So the purpose of this tutorial is to look at the ESD reliability in bulk FinFET technology, because the bulk FinFET has been the mainstream for CMOS technology in sub-20 nanometer node, right? And also the ESD reliability will strongly impact by the process option or technology option. Then besides of the ESD reliability, the I/O or related to the latch-up prevention is also another electrical issue which might be impacted by the process option in sub-20 nanometer node. So if we have a title, for sure we will cover this part. Then next to bulk FinFET, the gate-all-around device architecture will be the permission candidate for sub-10, even sub-7. Now should be sub-7 is a technology node. So in this tutorial, for sure, we will look at the influence of the device architecture and the process option, mainly on forward ESD diode behavior in this FinFET or gate-all-around device architecture. Okay, so after this tutorial, I hope that you will have a clear picture of this process option in FinFET or gate-all-around technology and how this process option impacting ESD diode performance or also impact the electrical immunity. But more important, we will look at the ESD challenge in future CMOS technology node, which might be this gate-all-around narrow wire or narrow sheet in sub-7 nanometer node. Okay. So it's the outline of my tutorial. First part is introduction. So I will introduce you how technology option impacting ESD diode performance, mainly based on our past learning. Then we will look at the ESD diode performance in state-of-the-art FinFET technology. First, we need to know what are the new process options in the state-of-the-art bulk FinFET technology. I think part of them already be covered this morning the presentation. But then we will compare the two different ESD protection diodes. They are Getty diode and the STI diode. Then we also will look at the proposed solution to further enhance the ESD diode performance in FinFET technology. As I mentioned, next to the bulk FinFET, the gate-all-around architecture will be a permission candidate for sub-7 nanometer or even sub-5 nanometer technology. So we will look at the ESD challenge in such technology node. Then if we have a title, we will cover the latch-up risk in bulk FinFET technology. Then final part is a conclusion. So let's start at the introduction. So as you might know, the technology innovation already setting the stage for ESD challenge. There are two immersion technology options on CMOS scaling roadmap. The first one is the device architecture moved from the bulk FinFET to get around the device architecture. Then the second thing is a high mobility channel material such as silicon germanium or even pure germanium will be integrated as a channel material to further enhance the functional transistor performance. But in order to protect this dedicated functional transistor, a robust ESD solution are required. And typically, the dual diode, as here showed, with an active power current, is most efficient ESD protection scheme in advanced CMOS technology node, because this ESD protection diode operate in the forward conduction mode. And this forward ESD protection, is locked. Which one?
There should be
It has been looking up. It should be. So try just using. Oh, it doesn't. No, it's not. PowerPoint just died. Oh, there we go.
Back. So then this forward conduction, the ESD diode need to sustain the target ESD current spec of 0.67 amp for 1 kV HBM ESD robustness. Then this forward operation, the ESD protection device also need to be operated inside the technology-defined ESD design window. Okay, sorry, should be here. Okay, the technology-defined ESD design window. And the typical ESD protection design window is defined between the normal circuit operation voltage, VDD, and the functional transistor breakdown voltage. So, and as here, you can see that the internal circuit breakdown voltage is significantly reduced by scaling the technology node. This makes the ESD protection design window become smaller and smaller. But not only this smaller ESD protection window, a newly introduced process option often result in the ESD diode performance degradation. I will show you some example in the following slide. So in the following slide, the 100 nanosecond TOP IT2 is related to the failure current, normalized by the layout width. It's used as a ESD diode performance index. So when the technology moved from planar to SOI FinFET, so the ESD diode performance dropped more than 20 times. Okay, the reason is related to first, it's a barrier oxide will significantly degrade the thermal dissipation, and then this barrier oxide will also kill the parasitic current passed in the bulk region. Then the fin structure will reduce the silicon volume on top, so that's why you get such huge degradation. And once the technology moves from the SOI FinFET to bulk FinFET, the ESD diode performance boost around 20 times. So the reason is related to this bulk silicon can create the parasitic current passed under the fin structure or even under the STI structure. And the fin directly connect to bulk region. This can enhance the thermal dissipation as well. Then once the landing pad removed, the ESD diode performance index also reduced around 50%. This landing pad is a planar-like active area, so it only exists in the very old FinFET technology. It's not existing in the nowadays FinFET technology. So the landing pad is used to connect the individual fin, and you also used for the contact landing. So this landing pad, once removed, it will also remove the parasitic STI diode between these two fin structures. So this process option has a strong impact on current distribution. The simulation result just showed. But first, the simulation result indicate no matter with or without the landing pad, like here shown, the most current still discharged through the fin structure because it has the shorter the current path. But with a landing pad, like here shown, the current can discharge under the STI region for this longer current path. So with a landing pad, you can see that it's like a gated diode in parallel with a STI diode. Okay, but once the landing pad removed, like here, then this parasitic planar-like the STI diode will be also removed. The 2D again locked. Okay, this the next I will make a cut line at the middle of fin. Then the 2D this cross-section view will give more information, but unfortunately it's locked again. Okay. Yeah, so you use this. Okay. So then the 2D cross-section view just showed under the STI region. Okay, the current density is much higher in the structure with the landing pad compared with the one without landing pad. Then let's make a cut line again just under the STI region to check the current uniformity. So then again with the landing pad, the current uniformity is much better compared with the one without landing pad. So with the landing pad, the total discharge current will be much higher compared with the one without the landing pad. Now let's rotate this fin structure 180 degrees. Look at the 3D from the fin side. Okay, then the fin side showed with the landing pad, there is a shorter current path from anode to cathode. This from anode to cathode. Then without landing pad, this current path become longer and also deeper. So without landing pad, will not only IT2 degradation, but also the R-on will significantly increase. So, okay, so as I mentioned, this ESD protection window becomes smaller and smaller. So then if the R-on increased, it will be very difficult to fit inside this smaller design ESD protection design window. Okay. The next thing, the failure analysis result just indicate. So no matter with and without landing pad, so the failure spot always locate at the fin structure just under the gate region. So it's quite consistent of the simulation result that I just showed you in slide 7. So no matter with and without landing pad, the most current clouding and the fin structure. So that's why they always the failure spot located at the fin under the gate region. But as I mentioned, there's a landing pad no more existing in nowadays FinFET technology. So let's move to the state-of-the-art FinFET technology. So again, there are several newly introduced process options in nowadays FinFET technology. So for sure, they will impact the ESD diode performance. So before we look at how they impact ESD diode performance, first let's check what's the main or the key process option in the sub-20 nanometer bulk FinFET technology. Here, I just mentioned, I will include 3 of them. The first one is the self-aligned double patterning for the fin definition. And the second one is the source-strained epitaxial silicon regold. These 2 process options will result in the fixed fin width and fin pitch. So this means only the limited area or limited volume contact to the buck region. So no more this planar light, the landing pad existed in the buck sub-20 nanometer buck FinFET technology. Then the third process option is related to the middle of light. It's a local interconnect with a silicide-less process option. So this process option will result in a localized contact area. So it's not a good sign for the ESD diode. So of course, all of them will impact ESD diode performance. But okay, so before we look at how they impact the ESD diode performance, let's look at more detail about these three process options. The first one is a positive self-aligned double patterning. So the litho pattern is not related to your final fin pitch. They will only related to your final fin, not related to your final fin width. They will only related to your final fin pitch or final fin spacing. So the litho pattern only transformed to the sacrificial hard mask. Then the following, there will be a spacer process. Then the spacer pattern will finally transform to the silicon region. Then the final fin width is defined by the spacer sideward length. Okay. So the final fin width is not a layout parameter, it's a processed parameter. So you cannot design your final fin width by the layout structure. Then the second process option is a selective epitaxial growth on source drain side, like here showed. So the purpose of this process option is first to increase the contact area by this diamond shaped on the surface, and also to incorporate with the dopant process. So during the epitaxial growth, in situ doping will happen. Then the third thing is this process option can be a strand material for the silicon channel. So by replacing the traditional silicon epi with this silicon germanium material. Then the third process option is related to the middle of light process. So it's the local interconnect with silicide-less process. So the middle of light structure is changed from the square type contact to stripe type local interconnect. Then the silicide process is also changed. So the traditional process is a silicide is the silicide is formed before the contact patterning or local interconnect patterning. But in the nowadays technology, it's not really worked. In nowadays technology, the silicide is formed after the local interconnect patterning. So only the opening region will form the silicide. So then this will cause the localized contact area. Okay, now let's look at the comparison. Okay, between these two different ESD protection diodes, they are Getty diode and the STI diode. So okay, these two types of ESD protection device, protection diode are studied here. So the first type is the Getty diode. In this Getty diode, the fins connect from the anode to cathode under this dummy gate structure. But in the STI diode, the fins are disconnected from anode to cathode. So these two different diodes will have two different current distribution. I will show later. But let's first look at the 100 nanosecond TOP measurement result. Okay, yeah, that really worked. Okay, now it's good. Sorry. Both. Okay. So the TOP measurement result just showed from the gated to STI diode, the IT2 can increase around 10 to 20%, but R-on will also increase around 30%. This is different IT2 and the R-on are related to different current distribution. The simulation result will show more detailed. So in the gated diode, a shorter current path can result in a lowered R-on. But this surfaced and short current path will easily induce the current clouding at surface, which will further result in the IT2 degradation. Then in STI diode, the current depth, the current path is deeper and also longer. So it for sure results in the higher R-on. But this vertical current path can prevent this local hotspot, so it will be benefit for the current uniformity. So this can get a higher IT2. Then let's look at the 2 nanosecond very fast TOP result. So this 2 nanosecond very fast TOP is usually to evaluate the ESD device under the CDM, charge device model, device behavior. According to the ESDA Industrial Council, the CDM, the charge device model, is the primary real-world ESD event in IC industry. So they are quite important. So then both diodes show a similar IT2 around 4 amp, and the STI diode shows slightly higher R-on, but not much. So the STI diode, in fact, no obvious drawback compared with the gated diode. But don't forget that the ESD is a changing event, especially when we study the CDM. So we need to look at the overshoot or the transient waveform. Then the measurement IV transient waveform just shows here. So with around 3 amp current stressed, both diodes can be turned on very fast. There is no overshoot at the beginning. Okay. So no, yes. Okay, so no overshoot for these 2 different types of the ESD diode. Now let's look at the layout parameter that impact ESD diode performance. So 3 layout parameters just studied here. The first one is a local interconnect number, stripe number in anode side and the cathode side. So with a fixed local interconnect pitch, the local interconnect number will corresponding to the fin length in the anode side on the cathode side. The second parameter is the gate length in the gated diode. So it designed same as the anode cathode distance in the STI diode. Then the third layout parameter is the layout width. So with a fixed fin width and fin pitch, the layout width is only determined by the fin number. So, and it's usually used for IT2 modularization. So more detailed design spread just showed here, okay? So let's first look at the impact of the local interconnect number on IT2. Okay, so when the IT2 normalized by the layout width, the IT2 is increased by increasing local interconnect number in both diode cases. But when IT2 normalized by the layout area, the IT2 actually is decreased by increasing local interconnect number, because increasing local interconnect number will also increase the fin length in either anode side or cathode side. This will increase your total layout area. So this result also indicates the current is not spread uniformly along the fin length direction. So then the small local interconnect number is a more area efficient design for ESD diode. But for the further fair comparison in the following slide, the local interconnect number is kept at the fold for other layout parameter, the split. Okay, now let's look at the impact of the gate length or the anode cathode distance. So in gated diode, the IT2 value current, diode value current, first increased by increasing the gate length from this small to the medium gate length. But finally it will saturate. This increase can simply be explained by increasing the surface balance resistance. Then in STI diode, so the IT2 is almost independent of the anode cathode distance because this STI diode has a vertical and deeper current path. You will be less impacted by the horizontal layout parameter. Then for the R resistance, so both diode types increased R by increasing the gate length or anode cathode distance. And in general, the STI diode has a 0.3 to 0.5 ohm higher the R. Again, I have mentioned a higher the R will be difficult to fit into a small ESD design window. So this problem for the STI diode need to be solved. Then the third parameter is the layout width. So the normalized IT2 just showed is independent of the layout width. So this just indicate the current, ESD current can spread uniformly along the width direction. So means that each fin can turn on during the ESD stress. Then the R can reduce by increase the layout width. However, if increase this layout width means the layout area will increase. It's a layout penalty. And also the parasitic capacitance will increase. So the parasitic capacitance increased will harmful to your circuit performance. So this needs to be prevented. So let's look at the impact of the parasitic capacitance in both diode cases. So first, in gated diode, the parasitic capacitance is almost independent of the gate length. Then for the STI diode, it's slightly decreased, but not much by increasing the anode cathode distance. Then in general, the STI diode has only 50% parasitic capacitance compared with the gated diode. So the smaller, it's much lower the parasitic capacitance make STI diode more permissive for high-speed application. Then let's look at the IT2, the parasitic capacitance in these two different diodes. So compare with the gated diode, the STI diode only have a 50% parasitic capacitance. Then with a 10 to 20% higher value current IT2, so the 10 to 20% higher the IT2, then this IT2 per parasitic capacitance will be more than 2 times higher in the STI diode. Then with a similar very fast TOP IT2, then but still 50% parasitic capacitance. So the very fast TOP IT2 per parasitic capacitance will be 2 times higher in the STI diode. So again, this excellent IT2 per parasitic capacitance make STI diode more permissive for high-speed application. So let's quickly align our gated diode result and the STI diode result in this ESD diode performance figure. So they look quite good. I mean, it's already approached to the old type the buck FinFET technology with this planar-like landing pad. But can we further enhance the ESD diode performance in this state of other FinFET technology? So I will show you some proposed solution. The first proposed solution is to take back this planar ESD diode in buck FinFET technology. Of course, this needs additional mask or additional process step. But anyway, the hypothesis here is from fin to the planar, around 70% surface silicon will be added on top. So it should be beneficial to IT2 enhancement. However, the measurement result just showed only 10% IT2 enhancement in by this planar ESD diode. So it seems to indicate this surface silicon value is not directly proportional to your IT2 level. So for the planar ESD diode, so they have only limited IT2 enhancement. So that's why in nowadays FinFET technology, you never see the planar ESD protection device. Then the second proposed solution is this deep implant ESD diode. The hypothesis here is increase the implant depth from the standard depth to deep implant can prevent the local hotspot inside this tiny thin structure. In addition, if the junction depth is deeper than STI structure, then you will go back to the planar region. So actually your junction is formed in this under the STI in this planar region. So you will enlarge the junction area with in the sand layout footprint. So then it should be beneficial to IT2 enhancement. However, the measurement result again show only 10% increase for STI diode, and even worse, no improvement for the Getty diode. So the reason again can be attributed to the different current distribution in these two different diode structures. In STI diode, the surface current will dominate, so it will be less impacted by the deep junction region. Okay, so there's no influence on the IT2. Then the STI diode, okay, we'll come next. Okay. I think I should prevent to use the laser directly on the file because it cannot follow. Yes. Okay, sorry. So then in STI diode, due to a deeper and vertical current path, so you will be impacted by this deeper junction region. So that's why you get this 10% IT2 enhancement. But the deep implant indeed has some benefit to the Getty diode. So, but only in the very fast TOP. I mean, very short, like a 2 nanosecond stress duration, because the deep implant can immediately force the current spread uniformly to this second local interconnect location, as here. So as here showed, the current uniformity along the fin will be enhanced by this deep implant. However, it only happened in very short time. Once you are stressed, your pulse width increased, the main local hotspot will still generate in this first local interconnect location. Okay. But this deep implant ESD diode will bring a strong or a serious negative impact on parasitic capacitance. We'll come in the next slide. So I think I will prevent using the laser directly in the file. Because you will see this laser is
Okay, so
stuck there.
let's see if we can switch it off.
Yeah.
Because that popped up before. PowerPoint failed.
Maybe in the meantime, have any question about the previous presentation? Yes.
So is there a reason why we are using a pentagonal shape for epi growth? Could it be any other pattern? Or?
I think if this is a diamond shape, your question is why we use this such like a diamond shaped epitaxial? Because this can increase this contact area.
So can we not grow a square? That will also increase the area.
But because it's a epitaxial, so you need to follow the crystal orientation, right?
Okay, so it's because of the crystal.
Yes. Yes.
I think some of it might be the animation. We've still got a few to go.
I think if I not use the
Laser, yeah.
in a file, that would be okay. But
Yeah.
if once I use the laser in the file, it would be difficult to.
Yeah. Sorry about that. Is that it?
Okay. Yes. Okay. Sorry. So, thank you.
No problem.
So as I mentioned, the deep implant will bring a significant or negative impact on the parasitic capacitance, especially in the STI die. Okay. So it will increase the parasitic capacitance more than 30%. So with just a 10% IT2 enhancement, but a 30% parasitic capacitance increased, the IT2 per parasitic capacitance actually is decreased by this proposed solution. Then with a similar IT2, then again this 30% parasitic capacitance increased. The very fast TOP IT2 per parasitic capacitance is also decreased. So this deep implant can increase the parasitic capacitance, so it's not a preferred option for high-speed application. So that's also a reason why you never see the deep ESD implant in the nowadays the FinFET ESD diode for ESD purpose. Then the third proposed solution is a wide city side based on previous two observation. A planar ESD diode or the deep implant ESD diode, they all have a limited IT2 enhancement. So this seems to imply the IT2 enhancement is regardless of the front end process. Then the stand along this back end layer, the IT2 can more than 100 milliamp per micron. So neither front end nor back end. So the bottleneck for IT2 enhancement will related to this local interconnect defined city side process. As I mentioned, this will generate or induce the localized contact area. Then this will further harmful your current spread uniformly along this thin length direction. Then with this proposed solution, wide city side, it should be benefit to enhance the current uniformity along the thin length direction. So it should be also beneficial to IT2 enhancement. But what's the measurement result showed? So measurement result showed this time indeed the IT2 can increase around 80%. So from this standard local interconnect defined city side to this wide city side. But this still needs to additional process or additional mask to define the list. So more detailed mechanism why this local wide city side can enhance the ESD diode performance will be disclosed in the following slide. So in this slide, the y-axis is the current ratio to the maximum current value. So for this standard city side, means the local interconnect defined city side, the peak to value difference is around 50%. But with this wide city side, the current uniformity is enhanced. So the maximum and the minimum value is only around 20% difference. So indeed, the current uniformity is enhanced. So it's positive to IT2 enhancement. However, as I mentioned, all of this process or the proposed solution that I show you is related to the processed solution. They all need additional process step or even additional mask. Then here I will show you I will show you the final proposed solution is called rotate diode orientation. So this is only the layout solution. There is no any additional process step or additional mask need. So be careful that I mentioned is a diode orientation rotate. It's not fin orientation rotate. So I will give you more detail. So from planar to FinFET, the diode orientation is kept. So the forward ESD current is from this N plus anode to this, so N plus anode to this P plus anode to N plus cathode. Okay, then once we regroup the fins like this, not two sides, but just this top and the middle. Okay, then your diode orientation then rotate 90 degrees. So your current path is also rotated from horizontal direction to vertical direction. What's the benefit to change the diode orientation or current path from along the fin structure to perpendicular to the fin structure? The 2D top view will give a simple explanation. So when the diode orientation rotates, so the current path will change from this tiny fin width to this extended fin length. So you will benefit for the ESD performance enhancement. So one thing that here I need to mention, this anode fin group and the cathode fin group, the distance need to be larger than 1 in order to prevent this different fin group merged by the epitaxial structure or shorted by the local interconnect layer. Okay, then the real simulation result just showed the R can be reduced around 20% by this rotated STI diode. So we can solve the STI diode R issued by this rotated diode orientation the solution. Then the simple explanation result is once we rotate the diode orientation, the effective diode width changed from this tiny fin width to extend the fin length direction. So you will be benefited for reducing the R of the ESD diode. Then the next question will be how many fins in each anode group, fin group and the cathode fin group will be most efficient. So a simple simulation result just showed the IT2 first increased by increasing this the fin number in each fin group. However, if you increase the fin number in each fin group, for sure your layout area will also increase. So the normalized result, the IT2 normalized by the layout area just showed around 4 fins will bring the highest IT2 result. So in this simulation, the anode and the cathode fin number are symmetric. If the 4th anode fin will be 4 cathode fin next to it. Then, but as I mentioned, this proposed solution is mainly used to solve the R issue. So we still need to look at the R result. Then the R will need to be around 5 to 8 will be the optimized result, because at this moment you will have a R at the low side but still have a reasonable IT2 per layout area. The next question is the dummy gate biased condition. So in order to keep the local, gate method density, the method, this dummy gate method need to be inserted in this rotated diode orientation. They are not functional, okay. They just are dummy in order to, keep the local, this metal density. But how we treat it, to tied to anode or tied to cathode or floating it. So a simple simulation result only include the thermal model, only include the electrical model but not the thermal model, just showed in this following slide. First, after certain distance or certain depths, the current uniformity will be very similar in different gap biased conditions. So for ESD, also the measurement result proved for ESD robustness, the IT2 level, there's no significant impact by different biased conditions. But the parasitic capacitance will be strongly impacted by different biased conditions. So here is the different biased condition, the analysis the result. When the dummy gate floating, the main parasitic capacitance will form the junction capacitance. But if the gate biased at the VDD, then there will be additional overlap capacitance that will be generated. So this will significantly increase the parasitic capacitance. But if it biased to the VSS, then a third parasitic capacitance element will be added on top. So it will further enhance the parasitic capacitance of this rotated STI diode. So for reduce the parasitic capacitance, better to leave the gate floating. Okay. Then let's quickly look at the IT2 per parasitic capacitance. Again, the smaller fin number will be good for IT2 per parasitic capacitance. However, if we still consider the R-on issue, so we still need to keep the fin number in each fin group, anode group, or cathode group at least larger than 5 to keep the R-on still at the low side and to get a reasonable IT2 per parasitic capacitance as well. So just give a quickly summary read in the state-of-the-art bulk FinFET ESD performance. The first, I already showed the technology or the process option has a significant impact on ESD diode performance. Then the STI diode is a permissive candidate for high-speed application because of the excellent IT2 per parasitic capacitance. Also, the STI diode in bulk FinFET show almost no overshoot, means it can be turned on very fast as the Getty diode. Then finally I show this rotated STI diode. It can further reduce the R-on, so it's a preferred ESD diode in bulk FinFET technology. I think in fact now the foundry they also use this rotated STI diode as a main ESD protection diode in the 16 or the 10 nanometer FinFET technology. Okay, so now let's move to the ESD challenge in future CMOS technology node. Okay. So next to bulk FinFET, the gate-all-around Nanowire or narrow sheet, this gate-all-around device architecture will be more permissive for the sub-7 or even sub-5 technology node. Then again, this new device architecture that will impact the ESD diode performance. So next we will look at how they impact the ESD diode performance. So this bulk silicon gate-all-around vertically stacked horizontal nanowire just showed here. Okay, here is a nanowire structure. Then they are simply based on the bulk FinFET technology, but with 3 additional process options. So they are ground plane implant, and the silicon germanium silicon germanium silicon epitaxial. And then the third one is a silicon nanowire formation. So the first process option is used to kill the parasitic channel at the top of the fin structure, just below these 2 silicon nanowires. Then the second process option is a silicon germanium silicon germanium silicon epitaxial is used to create the stacked 2 silicon layers. Then the real silicon nanowire is formed by etching out this silicon germanium layer. Then it's done in the RMG module just after this dummy gate removed, but before a real gate dielectric deposit. Okay. Now again, we still look at the 2 types of ESD protection diode, Getty diode and STI diode. Then in the Getty diode, the nanowire, these 2 stacked nanowire will also connect from the anode to cathode under the dummy gate structure. but there's no nanowire in the STI diode because I mentioned the silicon nanowire is formed in the RMG module, no gate, no nanowire. No dummy gate, no nanowire. In addition, the local interconnect defined the contact scheme with this titanium direct contact process option are used in these two different diode types. So the 100 nanosecond TOP result just showed the gated diode still has a lower R compared with the STI diode, but this time they have a similar IT2. Okay, put this R and IT2 result in the following slide with a 3D TCAD simulation. So in gated diode, this shorter current path results in a lower R compared with the STI diode has also longer and deeper current path. Then this time no current clouding at the surface. The highest current density moved to the bottom gate edge. Okay, so only little current discharged through this two narrow wired structure. So this can explain why the gated diode has a similar IT2 with a STI diode, because no current clouding and the surface is different from the FinFET gated diode. Now let's look at the total parasitic capacitance or total capacitive load in these two different diode structures. So the imaginary part of the admittance will directly proportional to the total capacitance load of the ESD protection diode. And from this iteration result, we can see the STI diode has a smaller capacitance load, especially in high frequency region. So let's look at more detail of this capacitance element in these two different ESD diode type. So here we use this two parallel capacitance model to emulate this parasitic capacitance inside these two different diode structures. The first capacitance element we call the overlap capacitance is determined by all the fixed capacitance between the anode and the gate structure in gated diode, and you will determined by the STI capacitance in the STI diode. Then the second capacitance element is the junction capacitance. Okay, so it's mainly from the PN junction, this junction capacitance. That's also in the gated diode. Then the iteration result here just show. The main difference is from the overlap capacitance. The gated diode has a 2 times higher overlap capacitance. So that's why the gated diode in total they have a higher parasitic capacitance. A more interesting comparison will be the FinFET ESD diode compared with the gate-all-around ESD diode. First, let's look at the gated diode. So the gate-all-around gated diode, the FinFET gated diode just show a lower IT2 and higher R, especially in high current region. Then the similar result also showed in the STI diode. So the higher the R is always showed in the high current region. So this difference between the gate-all-around ESD diode and the FinFET ESD diode can be first related to the additional process option of the ground plane implant I have showed in the slide 15. Okay. So, but the measurement result just showed there's almost no impact for the different ground plane implant concentration in both diode type, gate-all-around gated and the gate-all-around STI diode. They have a very similar IT2 and R. However, this ground plane implant will significantly increase the parasitic capacitance due to the higher dopant concentration and the diode PN junction interface. So these two green curves here just showed in both diode cases the parasitic capacitance will significantly increase by with this ground plane implant. So for the STI diode, it can increase around 40%. For Getty diode, it can increase around 50%. So then, in addition, the total capacitance load in Gate-All-Around ESD diode and the FinFET ESD diode, they look quite similar. So it's not related to additional process option of this ground plane implant. Then what's the root cause for the difference between the Gate-All-Around ESD diode and the FinFET ESD diode? The TCAD simulation result will show more detailed information. First, in the FinFET Getty diode, the current will clouding at the surface. So this can be the reason why the FinFET Getty diode has a lower IT2 compared with the Gate-All-Around Getty diode. Then also in the simulation result here, just indicate the ground plane implant seems to have an impact on the current density inside the narrow-wired structure. I know the color code looks not so, the difference looks not so obvious, but in fact you still can see the color code different in these three different ground plane implant conditions. However, the further analysis result just indicate less than 5% ESD current will discharge through this narrow wire structure. Almost 95% will discharge through this parasitic channel at the back, under this narrow wire structure. Then for the ground plane implant, so with the same gate length, the ground plane implant impact will less than 2%. Then with the same ground plane implant, the gate length impact will also around 3% only. But on the other hand, in the FinFET Getty diode, more than 12% ESD current will discharge to this tiny fin structure, and the most of them will clouding at the surface. So this is the reason why the IT2 is lowered in the FinFET Getty diode. Now let's look at the STI diode. First, the the ground plane implant only has a slight impact on the current distribution inside this fin structure, because the ground plane implant is shallower than the STI depth. So finally, they have no impact on the IT2 and the RR in the STI diode. Then, in addition, this STI diode, Gate-All-Around the STI diode, looks very similar to the FinFET STI diode. So, but as I showed, the TOP result just indicate at a high current region, the RR is higher in the FinFET STI diode compared with the Gate-All-Around the STI diode. So the root cause is related to the different self-heating behavior in these two different STI diode structured. This can be further proved by the long pulsed TOP result, as shown in this slide. So when the TOP pulsed width increased, this means the more energy that will inject into your device. So this more energy that will make the self-heating more pronounced. So then in the FinFET STI diode, the R increased by increasing the TOP pulsed width. But in the same time, the TOP pulsed width seems almost has no impact on the R in the Gate-All-Around the STI diode. So this already shows two different self-heating behavior in these two different STI diode structure. The root cause related to this different self-heating behavior is related to the fin height difference. In order to get this stacked narrow wire structure, the fin height will be totaled in the Gate-All-Around technology. And usually a total fin will accompany with a larger epitaxy volume. so which is beneficial for contact skin and also beneficial for thermal dissipation. So better thermal dissipation means the less self-heating the issue. So that's why you didn't see the R increased by increasing the pulse width. Then the simulation result further prove it. So as I mentioned, due to a total fin height in the gate-all-around the STI diode, so it has a larger the epitaxy volume. It's beneficial for contact skin and also beneficial to the thermal dissipation. So then the lattice temperature will be much lower in this total fin height gate-all-around the STI diode compared with the one with a FinFET STI diode. Then the further analysis result just indicate under 100 nanosecond TOP stress, the maximum temperature difference can be around 150 K. So this temperature difference will, less the heat generator can prevent the self-heating the issue and to increase your R, to prevent the R increased in the total fin height gate-all-around the STI diode. And besides the fin height difference, so the STI depth might be also different in this future technology node, because if the fin height increased, in order to keep a reasonable aspect ratio in the STI module, the STI depth might need to be reduced. So this slide just showed the impact of different STI depths. So from the 40 nanometer STI depth to the 80 nanometer, the temperature can increase more than 300 K. So this means you will have IT2 degradation, because it will be easily to induce the local hotspot in your STI diode structure. And also the R will increase around 8%. So here just a summary figure. So when the fin height increased or the STI depth reduced, both are benefit to reduce the maximum temperature or the average temperature. So they are good side in the future technology. However, all of these results are mainly based on the one fin structure. So we are discussing one fin at this moment. So if we consider the fin pitch also scaled, the story might be different. I will give you some examples in this slide. So first, if the fin pitch is fixed at 45 nanometer, this means there is like a 16 or 14 nanometer FinFET technology, right? And the fin height is a 30 nanometer to the 50 nanometer. Your epitaxy value will increase due to a total fin. So then your contact area or contact depth will increase by increasing the fin height. But once your fin pitch further scaled, okay, then the epitaxy structure between two fins will merge. So this will reduce your contact area between the two fins, or reduce your contact depth between the two fins structured. So a total fin and a smaller fin pitch will result in your contact depth reduced, and also this the one fin epitaxy structure will also reduce because the epitaxy structure will merge. Then the contact depth will have a strong impact on this maximum temperature, or it will easily to induce the local hotspot. So for example, if the contact depth reduced to the 10 nanometer, the temperature will increase around 70%. Then with a standard contact depth, the epitaxy value will have a less than 10% impact by increasing this maximum temperature. So the key thing will be the contact area. So that's why the extremely case is with this rim around contact. This means that without any epitaxy, you just contact it by rim around this source drain side. Okay, so in fact, the maximum temperature can reduce to around 20% without any epitaxial structure. However, this process is still quite difficult in nowadays technology. Okay, but this will be benefit also for the functional transistor. So I think that it will be a goal to go with a run-around contact. But so it's a good news for ESD diode because it will also reduce the maximum temperature for ESD protection device. Then let's quickly look at the 2 nanosecond very fast TLP result. Okay, also compare with the FinFET ESD diode and gate-all-around ESD diode. Again, this FinFET one always show a lower IT2 and higher the RR, especially in high current region. Okay, then so in FinFET also we can see that the gate diode and STI diode they have a similar RR, but in the gate-all-around we can see the gate diode has a lower the RR. For the explanation in the gate-all-around this time, so the previous I just show you the gate diode and the STI diode in the gate-all-around technology that they have a similar IT2. But in the 2 nanosecond very fast TLP result, the gate diode shows slightly lower the IT2 compared with the STI, the gate-all-around STI diode. The reason is related to the time dependence, the current distribution in the gate-all-around gate diode. So here I just show you at the beginning the most current, like the 50 picosecond, the most current discharged through the top nanowire structure. And when the stress tide increased, the current will spread to the second one, and finally it will go through this parasitic path under this 2 nanowire structure. But it might be happen when the stress happen. When the stress happen at the beginning, it will burn out this narrow, tiny narrow wire. So that's why the gate-all-around gate diode has a slightly lower IT2 compared with the gate-all-around STI diode. The similar thing also showed in the FinFET gate diode, but so at the beginning the current will already go through the surface, but then the current ratio will increase when the stress time increased, and finally the 12%, around 12% will discharge through this fin structure, but like 87% will discharge through this parasitic path under the fin structure. Then the further analysis result just indicate this degradation, I mean this current ratio, the degradation will be more pronounced in this gate-all-around gate diode. So that's why the gate diode in the gate-all-around structure will still, I mean, they have a still slightly higher IT2 compared with the FinFET gate diode. Okay, but then the R-on is not real beneficial by this surface current path. Why? Because if the current clouding at the surface, it will induce this self-heating issue, as I mentioned, this self-heating issue. So the self-heating issue will be more pronounced in the FinFET gate diode compared with the FinFET gate-all-around gate diode. Okay, a similar result also showed in the STI diode. They have more, I mean, the cam voltage will increase. This indicates the self-heating happened. But it's only happening in the high current stress at the 3.5 amp. If in the low current stress, the self-heating issue is not so pronounced in both tile cases. So this further proved what our simulation results showed. So during the stress, due to the different fin height and different epitaxial structure, so their self-heating behavior will be different, especially in the high current stressed region. So then in 2016 IDM, okay, so 7 nanometer the CMOS technology already be published. I mean, but here I think there are one common thing is they all mention the channel strength, but they are implemented by different methods. In this paper, it mentioned it's used the dual epitaxial process to optimize this strand. But in another paper, okay, so the channel strand is from the substrate, and even for the PMOS, the channel material is changed. Okay, so let's look at how this source strand will impact the ESD diode performance. Okay, so here I just show these two different STI diodes with a different source strand epitaxy. One is the traditional silicon epi structure, and with implant, very traditional process. Then another one is a silicon germanium epitaxy structure with in situ boron doped. Okay, then the gated silicon germanium diode is inserted for the comparison. So in both this silicon germanium gated and the STI diode, they have a lowered turn-on voltage. Okay, the ringing view we just showed here. Then more interesting thing observed in the silicon germanium STI diode. So they will show the initial higher the R-on, and then it just jump back. It look like a snapback, but the snapback should not happen in the forward ESD diode, right? So that's why we also confirmed it by the DC measurement result. First, the DC measurement result also showed the silicon germanium gated and the STI diode they have a low turn-on voltage. And only in the silicon germanium STI diode, we see this initial higher on resistance. Okay, so all of this is related to the interaction between the heat transfer structure interface and the junction interface, as I showed here. This interaction between this silicon germanium and the silicon heat transfer structure interface and the PN junction interface will impact this interface band diagram. So different band diagram will bring this different device behavior. For example, if you have this junction interface aligned with the silicon germanium silicon heat transfer structure interface, then there will be a valence band offset, obvious valence band offset. So this will be a barrier for the whole conduction. So that's why you will get this higher resistance. Okay. So, but this can be also solved by this scenario. Once your junction is deeper than your heat transfer structure interface, then this valence band offset will be reduced. So there will be no energy barrier for the whole conduction. Okay. Then here just a strand from this silicon source strand silicon germanium epitaxy. But if the channel material change to like a silicon germanium or silicon, what's the impact? Again, this silicon germanium or germanium, the interface between the heat transfer structure interface between this silicon germanium or germanium and the silicon will induce the heat transfer structure isolation. So this will further induce the current clouding at the surface. Okay, because the valence band offset you hold will be preferred to stay at the low energy at the surface. And even worse, if the relaxed this bulk region by the silicon germanium, they will induce the additional thermal isolation because the silicon germanium, this alloyed, this alloying material, the thermal dissipation will be less than the pure silicon or pure germanium. So it will induce additional thermal isolation in this structure. Then in 2017, the IBM proposed the beyond 5 nanometer or 5 nanometer or beyond 5 nanometer technology. They proposed this stacked horizontal narrow sheet structure. So here they already mentioned that it's a run around contact. And an additional process option they mentioned is the dielectric isolation. What's the impact for this dielectric isolation? I will show you later. But why we want to go to this narrow sheet? Because this stacked narrow sheet will enhance your effective channel width. So it's a benefit for the functional transistor performance because it will increase the effective width. And in this paper, the conclusion is a 3 stacked narrow sheet is necessary to compare with the nowadays FinFET technology. Okay, then as I mentioned, so this newly introduced process option in this paper is a dielectric isolation. So in order to kill this parasitic channel here, okay, at IMEC we use this, we call it the ground plane implant. So we just increase the dopant concentration here and we make this a VT higher. So then you will not see in the normal circuit operation, you will not see this channel here. But in order to totally kill this parasitic channel here, so this paper proposed a dielectric isolation. It means that your source drain will be stopped at this region. So there will be no electrical connection between these two. But this dielectric isolation will make there will be no parasitic buck diode in this in this process option. So then we will go back to this SOI type device. But this will be, to significantly deteriorate our ESD diode performance. So we need to deal with a different story now. And should I stop here or I continue? Continue. Okay. So then the next, besides of the ESD reliability, latch-up is also a concern in the nowadays the FinFET technology. So I think that I will skip this one. So I will quickly introduce what's the latch-up. So the latch-up structure is inherent in the simple inverter structure. So it's from the PMOS the source to the NMOS the source. There will be a PN SCR path between the VDD and the VSS. So once this device turns on, you will have a strong current leak from the VDD to VSS. Then the latch-up criteria, once it's triggered, in order to keep in the latch-up state, there are 2 criteria. The first one is your NPN and a PNP bipolar gain product need to be larger than 1. The second thing is your holding voltage will need to less than your operation voltage VDD. Then you can keep it. This structure will keep it in the latch state. So then we further studied this parasitic PNP and SCR path or latch-up path in the FinFET technology, and also we compared with the similar structure in planar technology. Okay, first let's look at the parasitic NPN and PNP bipolar gain. So if you have a lowered bipolar gain, for sure your latch-up risk will be less, right? And during the simulation, it's not simulation, it's a measurement result just showed. In the NPN and the PNP, the FinFET NPN and PNP, they both have a higher bipolar gain compared with the planar PNP and the NPN bipolar. So the main reason for this is related to the different STI depths. As I mentioned, so in order to keep a reasonable aspect ratio for the STI process module, so the STI depth will reduce from the planar to the FinFET structure. So this can further proved by illustrated a vertical resistance in unveiled resistance. So from this measurement result, we can see that this vertical resistance will be 4 times higher in the planar technology. Means that your STI depth will be much deeper in the also in the planar technology. And the similar observation or similar this latch-up issue is also showed in the, this is from Silence, I think, their real product. So but it's a different latch-up test. It's a single event latch-up. But in their product, they indeed see the FinFET has the highest latch-up issue compared with the planar technology. So then, as I already mentioned, the main reason is because the STI depth is quite different in the planar and the FinFET technology. So the STI depth becomes shallowed from the planar to FinFET. Then the simulation result just showed different STI depth can enhance your bipolar gain product more than 5 times. And I just show you the previous measurement result shows more than 10 times the increase in these 2 different technology with different STI depths. Okay, so this brings me to a conclusion. So in this presentation, I already show you how technology option impact ESD diode performance. But the ESD will not a showstopper or will never be a showstopper even in the future the technology. Okay, so we always need to find a solution for the ESD. And the second thing is the rotated STI diode is the preferred ESD protection device in nowadays the back FinFET technology. I think it will be also for the future the FinFET technology. Then for the ESD diode in the back ghetto around the Nanowire technology, again the STI diode is still a better candidate due to the excellent attitude per parasitic capacitance. However, the additional process option, this is a ground plane implant, will significantly increase your parasitic capacitance. So this need to also be dealt. Then in general, the back ghetto around the ESD diode shown no disadvantage compared with the back FinFET STI diode. Then I just showed the latch-up still is an issue, even increased the risk in the back FinFET or ghetto Nanowire technology because your STI depth becomes shallower and shallower. So the final thing I would like to mention, all of this trend or different material, so they will bring this heat structured isolation or different this band diagram, this disconnect issue. So they will be a challenge for the future technology node. Okay. So here I just simply show. Here I just simply show you some this scaling technology roadmap for at the IMEC. Okay. So now we are already in this technology and design the technology called optimization. So soon we will move to the system and technological optimization area. So then the stacking issue we still also need to deal. But unfortunately, I didn't cover it in this presentation. But I think for the future technology, this still need to be looked for ESD challenge. So, okay, so this is all my presentation. Thank you.
So, open for questions?
I have a quick question.
Yes.
Is Proceed STI kind of diode also working all around the kind of structures?
Yes, because this rotated STI diode is mainly used for STI diode. So once you still keep, if you not use the dielectric isolate, then this will be also worked for the gate-all-around technology. Yeah.
Can I have a question?
So for the rotated diodes, is there going to be a deep implant diode for that too, or do we have benefit if we were to do a deep implant for the rotated diode?
No. I don't think it's necessary to go to deep implant because deep implant, the main issue that they will increase your parasitic capacitance. I don't think it's a benefit to use it.
So, how does the parasitic capacitance compare between a normal STI diode and a deep implant and a rotated diode?
I think so.
So a normal
Yes.
STI diode and a rotated STI diode. So how does the parasitic capacitance compare between those two?
I think they will not have a strong impact like my table showed. Maybe I can quickly go to 5. Yeah, here. Okay, so the parasitic capacitance, in fact, is slightly increased. However, because your IT2 will also equally increased. So IT2 per parasitic capacitance actually is not really changed from the normal STI diode to the rotated STI diode. So they are it's still okay. You will not increase the parasitic capacitance there. But if you also consider the deep implant, for sure, this will be increased again.
Okay. But we will get the benefit of the uniformity of the current flow that we get from the implant, right?
Yes, but only very short, stressed duration. For the long term, especially for the long stressed for the Getty diode, there is still an issue for the shortest path issue. Okay.
In the measurable ESD performance, can you give an estimate how much those new processes compared to conventional kind of CMOS to in the future to need to lower the requirement?
Yeah. So your question is these are all of the technology, the impact will finally lowering the ESD the standard, the ESD requirement labeled. I think always in the ESDA, the standard meeting, they always discuss the list. But I would say that for the HBM, nowadays it's not really a challenge. I think that they still can to get like a 500 volt or even 1 kV is still no problem. But the main challenge is from the CDM. Because the charge device model, as I mentioned, there will be a real primary ESD event in nowadays, the IC industry. So in fact, they are discussed to reduce the CDM, but not only because of the technology issue, but also because your package become bigger and bigger. And this charge device model will strongly impact by the parasitic the capacitance from your package. So if your package become bigger, in the same stressed voltage or charge voltage, your peak current will become the higher or even larger. So this is an issue. So I think in standard meeting they really discussed to rolling this requirement label in future, but not only because of the technology, but also because of all this stacking and the package. Many systems will integrate in the same die store. This will be an issue.
Okay. Any more questions? So just about perfectly on time. Thank you, and thank you for staying to the end of the session.